Hello there, and welcome to Sleepwalk Space. Tonight, we drift into the ancient and extraordinary world of geology, the deep memory of our planet written in stone. Long before stars were named or oceans had boundaries, the Earth was already alive, reshaping itself in silence. Mountains rose and crumbled, seas vanished and returned, continents wandered across glowing oceans of rock. The ground beneath you is ancient beyond imagination, and yet it is still moving, still breathing, still changing. This is the story of geology, a story of fire and water, of creation and collapse, of beauty that takes millions of years to unfold. Beneath every step, within every pebble, there are whispers of volcanoes, glaciers, and stars long gone. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the ancient earth cradle your thoughts. Let's begin. The ground you stand on floats like a raft on molten rock. Beneath the thin crust lies the mantle, a vast region where rock flows like honey over geological time. The continents rest on this mantle like enormous rafts of stone, drifting slowly across the surface. They move at rates of only a few centimeters per year, but over millions of years, those tiny movements reshape the entire world. Oceans open and close. Mountain ranges rise and climates transform. The continents we know are travelers, always in motion, though the journey is invisible to us. This slow drifting is what once united all land into the supercontinent Pangaea, and will one day bring the continents together again. Our planet is alive beneath its calm surface, and we are passengers on its vast, drifting plates, carried across geological seas without ever feeling the motion. Every grain of sand was once part of a mountain. Each tiny grain of sand once belonged to something far greater. Long before it rested on a beach or desert, it was part of a towering mountain or an ancient bedrock plain. Over millions of years, wind, water, and ice ground that rock down to its smallest possible pieces, carrying them across rivers and seas. A single grain might have tumbled through glaciers, flowed down canyons, or drifted across oceans before coming to rest. Under a microscope, its shape and composition reveal the kind of rock it came from and the journey it took. Some grains still shine with fragments of quartz from ancient continents. Others are volcanic shards from fiery eruptions long past. Every handful of sand is a storybook of time, a collection of broken worlds reduced to glittering fragments that will one day be pressed back into stone and start the cycle again. Mountains are constantly being built and worn away at the same time. What appears to be eternal is actually caught in a battle between creation and destruction. Deep below, tectonic forces push rock upward, adding height to peaks, millimeter by millimeter. At the same time, wind tears at exposed surfaces, rain dissolves minerals, and ice fractures stone into smaller pieces. Glaciers grind valleys deeper, while rivers carve canyons through solid rock. The mountains we see today are temporary forms in an endless cycle. The Himalayas rise by a few millimeters each year, while simultaneously shedding material that becomes sediment in distant oceans. Over tens of millions of years, even the tallest peaks will erode away completely, their remains scattered across the planet. Yet, new mountains will rise elsewhere as plates collide and continents shift. The landscape is never finished, only paused in a moment we happen to witness. Rock can be older than complex life itself. Some of the stones beneath our feet formed long before the first animals swam in ancient seas. Rocks dating back 3.5 billion years still exist on Earth's surface, preserving a record of a world utterly unlike our own. When these stones solidified, the atmosphere contained almost no oxygen. The continents were barren, devoid of plants or creatures. Only simple microbes existed, building layered mats in shallow water. These ancient rocks witnessed the slow transformation of the planet from a lifeless sphere to a living world. They survived the rise of oxygen, the freezing of entire oceans, the assembly and breakup of multiple supercontinents. To hold such a rock is to touch something that predates nearly all the complexity we take for granted. It carries within its crystalline structure the memory of an Earth so different it would be unrecognizable, yet it is still here, patient and enduring. Lava can flow faster than a person can run. When we imagine lava, we often picture slow rivers of glowing rock, advancing with patient inevitability. While this is true for many eruptions, some lavas are shockingly fast. Basaltic lava, low in silica and high in fluidity, can race down slopes at speeds exceeding 30 kilometers per hour. During major eruptions in Hawaii and Iceland, lava flows have overtaken roads and buildings before people could react. The speed depends on the lava's temperature, composition, and the steepness of the terrain. Thinner, hotter flows move like water, cascading over obstacles and flooding valleys in hours. Watching such a flow from a safe distance is both beautiful and terrifying. The orange river glows against the darkening sky, hissing and crackling as it consumes everything in its path. Yet within days, it cools to black stone, adding new land to the Earth's surface and beginning its slow transformation into soil. Some rocks float on water. Pumice, a volcanic rock formed when lava cools rapidly while filled with gas bubbles, is so light and porous that it floats. After explosive eruptions, vast rafts of pumice can drift across oceans for months, traveling thousands of kilometers before washing ashore. These floating islands of stone carry seeds, organisms, and even small animals to distant coastlines, helping spread life across isolated islands. Sailors have reported encountering pumice fields so dense they slowed ships to a crawl. The rock's surface is rough and abrasive, riddled with countless tiny holes that once held superheated gas. Despite being solid stone, pumice contains more air than rock by volume. Over time, waterlogged pieces sink to the ocean floor, settling into layers that become part of the geological record. To hold pumice is to feel the paradox of stone lighter than water, a reminder that even the heaviest element of Earth can, under the right conditions, defy its nature. Earth's oldest mountains have been ground down to gentle hills. The Appalachian Mountains, once as tall as the Himalayas, have spent hundreds of millions of years eroding. What remains are rounded, forested slopes that hint at their ancient grandeur. These mountains formed during the collision of continents long before Pangaea assembled, when the world's geography was unrecognizably different. The forces that built them were just as powerful as those raising the Andes today, but time has softened every peak. Rivers carved through uplifted rock, glaciers scraped valleys smooth, and rain dissolved minerals grain by grain. The material removed from these mountains now lies in sediments across the eastern seaboard, layered in rocks that tell the story of their slow destruction. Yet the roots of the mountains remain, deep and strong, their ancient cores still visible where erosion has cut through to reveal billion-year-old stone beneath. Minerals can grow inside living organisms. Some creatures build their bodies from minerals extracted from water and food, creating structures of astonishing beauty and strength. Mollusks construct shells from calcium carbonate, layering it into shapes of spiral perfection. Coral polyps do the same, building reefs that stretch for thousands of kilometers. Even within our own bodies, bones and teeth are mineralized structures, grown through biological processes that mirror geological crystallization. Some bacteria can produce magnetic crystals inside their cells, using them to orient themselves in water. Sea urchins grow calcite spines with crystalline precision. These biological minerals blur the line between living and non-living, showing that geology and biology are deeply intertwined. When these organisms die, their mineralized remains become sediment, which over time compresses into limestone and other rocks. The stone we see in cliffs and quarries often began as countless tiny lives, each one building its body from the dissolved geology of the sea. Deserts can sing in the wind. Across certain sand dunes, a mysterious phenomenon occurs. When conditions are right, the dunes produce deep, resonant hums that can last for minutes. These singing sands, found in deserts from the Sahara to the Gobi, create notes so pure they sound like the voice of the earth itself. The sound comes from countless grains sliding and colliding in unison, vibrating at specific frequencies. Scientists believe the grains must be nearly uniform in size, perfectly dry, and rounded by wind to produce this effect. Travelers describe the experience as haunting, as though the landscape is breathing or speaking. Ancient peoples often treated these sounds as mystical, believing they came from hidden spirits or desert gods. In truth, it is physics and friction working together, turning the landscape into a natural instrument. The dunes sing the slow, patient music of shifting earth, a melody that has resonated across deserts for millennia. Glaciers are rivers of solid ice that flow like liquid. Though frozen, glaciers are not still. Under the pressure of their own immense weight, ice crystals deform and slide past one another, allowing entire masses to creep downhill. This movement gives glaciers their fluid grace, their ability to carve mountains and shape valleys over tens of thousands of years. The flow is fastest at the surface and center, slower along the edges and bottom, where friction holds the ice back. Deep within a glacier, where pressure is immense and temperatures hover just below freezing, ice stops behaving like a brittle solid and becomes something closer to slow-flowing honey. Crevasses form where the ice stretches over uneven terrain, opening blue chasms that reveal layers accumulated over centuries. To stand on a glacier is to stand on moving time, a frozen river that carries the memory of ancient snowfalls toward the sea. Some crystals take millions of years to form. Deep underground, in conditions of perfect stability, crystals can grow to extraordinary sizes. The largest require millions of years of uninterrupted growth, molecule by molecule, as mineral-rich water seeps through rock. The Cave of Crystals in Mexico contains gypsum formations more than 10 meters long, each one a testament to geological patience. These translucent giants formed when superheated groundwater remained at a steady temperature for hundreds of thousands of years, allowing molecules to arrange themselves with perfect symmetry. When the cave was drained, the growth stopped, freezing the scene forever. Elsewhere, quartz crystals the size of tree trunks have been discovered in granite chambers, their faces flat and geometric, reflecting light with mathematical precision. Each crystal is a time capsule, its growth rings recording subtle changes in chemistry and temperature. To see one is to witness the power of patience, proof that given enough time, even molecules can build monuments. fossils preserve moments that lasted only seconds. While most fossils capture organisms that died and were buried slowly, some preserve fleeting instants. Fossilized raindrops mark storms that passed hundreds of millions of years ago, their tiny craters still visible on ancient mudstone. Footprints of dinosaurs crossing wet ground have hardened into permanent records of single journeys. Ash falls from volcanic eruptions buried forests so quickly that leaves remain in perfect detail, their veins and edges sharp. In some fossils, you can see the ripples of water frozen in stone, the last wave pattern before sediment covered the surface forever. These snapshots of time reveal moments that lasted seconds but have endured for eons. They remind us that geology preserves not just long, slow processes, but also the briefest flickers of activity. Every instant of Earth's history has the potential to become eternal when conditions align to turn soft sediment into hard stone. Water carved the Grand Canyon over millions of years. The Colorado River, flowing steadily through the same channel for more than 5 million years, has cut through layers of rock nearly 2 kilometers deep. What began as a stream on gently rising land became a powerful force of erosion as the plateau beneath it slowly lifted. Year after year, century after century, the river carried away sand, silt, and stone, exposing bands of color that represent different geological ages. The oldest rocks at the canyon's bottom are nearly 2 billion years old, while the youngest layers at the rim formed only a few 100 million years ago. Walking down into the canyon is like descending through time itself, each layer a page in Earth's history. The river continues its work today, still carving, still deepening, moving imperceptibly toward some future form we can only imagine. The canyon stands as proof that patience and persistence can reshape even the most solid stone. Earthquakes can make the entire planet ring like a bell. When the largest earthquakes strike, they send seismic waves rippling through the Earth's interior and around its surface. These waves cause the entire planet to vibrate, oscillating at frequencies too low for humans to hear, but detectable by sensitive instruments. After a magnitude 9 earthquake, the planet can continue resonating for weeks, its crust flexing and relaxing in slow rhythm. Scientists call these oscillations free oscillations, and they reveal information about the structure of the deep Earth. Different frequencies travel through different materials, allowing researchers to map the boundaries between the crust, mantle, and core. In this way, earthquakes become tools for understanding what lies beneath our feet. The planet rings with its own deep notes, a harmonic signature that speaks of its internal structure. Every great quake is both destruction and revelation, violence transformed into knowledge. Volcanoes can erupt underwater without anyone noticing. Far beneath the ocean's surface, along the mid-ocean ridges, volcanic eruptions occur constantly. Most go unnoticed by humanity, hidden beneath thousands of meters of water. These submarine volcanoes build new seafloor as magma wells up through cracks in the crust, cools, and solidifies. The process is usually gentle, with lava oozing out in rounded pillows rather than explosive blasts. Occasionally, larger eruptions send plumes of superheated water and minerals billowing upward, but they rarely reach the surface. Some underwater volcanoes grow tall enough to become islands, breaking through the waves after thousands of eruptions. Others remain submerged, forming seamounts that rise kilometers above the ocean floor, yet never see sunlight. These hidden fire mountains are among the most active volcanic systems on Earth, continuously reshaping the seafloor in darkness and silence. Limestone is made from the shells of ancient sea creatures. The white cliffs of Dover, the limestone buildings of ancient cities, and the marble floors of grand halls all began as living organisms in ancient seas. Countless trillions of tiny creatures, from plankton to coral to mollusks, built their bodies from calcium carbonate dissolved in seawater. When they died, their shells and skeletons settled to the ocean floor, accumulating in thick layers. Over millions of years, the weight of overlying sediment compressed these remains into solid rock. The process continues today in shallow tropical seas where limestone is still forming. When you see a limestone cliff, you are looking at billions of lives compressed into stone, an archive of ancient oceans preserved in mineral form. If you examine it closely, you might still see shell fragments and fossil outlines, hints of the creatures whose remains built the rock. Some geodes are hollow caves lined with crystals. Within ordinary-looking rocks, hidden chambers sometimes sparkle with crystalline beauty. Geodes form when gas bubbles in cooling lava create hollow spaces, or when groundwater dissolves pockets within sedimentary rock. Over time, mineral-rich water seeps into these cavities and slowly deposits crystals on the inner walls. Layer by layer, the crystals grow inward, creating druzy surfaces of quartz, amethyst, or calcite. The largest geodes are big enough to stand inside, their walls encrusted with thousands of sparkling points. Smaller ones fit in your palm, their weight surprisingly light because of the hollow core. Breaking open a geode is like discovering a secret. The rough exterior gives no hint of the glittering interior. Each one is a tiny world of geometry and color, proof that beauty often hides in unexpected places, waiting patiently to be revealed. The Sahara Desert was once a lush, green savanna. Thousands of years ago, the world's largest desert was covered with grasslands, lakes, and forests. Ancient rock art in the Sahara depicts hippos, giraffes, and elephants, animals that require water and vegetation to survive. This green Sahara existed during a period when Earth's orbital variations brought more rainfall to North Africa. Rivers flowed through valleys that are now dry wadis. People hunted and fished where today there is only sand. Around 5,000 years ago, the climate shifted. Monsoons weakened, vegetation died, and the desert expanded. The transformation happened relatively quickly in geological terms, within a few centuries. The sand now covering the region once formed the beds of ancient lakes and rivers. Beneath the dunes, satellites have detected dried riverbeds and buried aquifers, remnants of that wetter world. The Sahara reminds us that climate is never static, that landscapes we consider permanent are only temporary arrangements in the long dance of Earth's changing face. Rocks can record the direction of ancient magnetic fields. As lava cools and solidifies, iron-bearing minerals within it align with Earth's magnetic field like tiny compass needles. Once the rock hardens, those alignments are locked in permanently, preserving a record of the field's direction at that moment. Scientists can measure these ancient magnetizations to determine where the rock formed and which direction was north at the time. This technique, called paleomagnetism, has revealed that continents have drifted across the planet and that the magnetic poles have reversed hundreds of times throughout history. Some rocks show that they formed near the equator, but now sit near the poles, carried there by the slow movement of tectonic plates. Others record magnetic field directions that point south instead of north, evidence of ancient reversals. the invisible magnetic field that guides migrating birds and human compasses has left its signature throughout the geological record, written in stone by iron and time. Diamonds can form from buried organic material. While most diamonds crystallize deep in the mantle from pure carbon, some may form from organic material dragged down into the earth. When tectonic plates collide, sediments on the ocean floor, including the remains of ancient life, can be pushed deep into subduction zones. There, under extreme heat and pressure, the carbon in these organic remains can be transformed into diamond. The process takes millions of years and occurs at depths greater than 150 kilometers. When volcanic eruptions bring these diamonds upward through kimberlite pipes, they carry with them a strange history. The carbon that now sparkles in jewelry may once have been part of an ancient plankton, a prehistoric plant, or sediment rich in organic matter. Each diamond is a transformation story. Ordinary carbon subjected to such intensity that its atomic structure reorganizes into the hardest natural substance on Earth. Mud cracks from ancient droughts have turned to stone. In dried lake beds and mudflats around the world, geologists find rocks covered with polygonal patterns. These fossil mud cracks formed millions of years ago when wet sediment dried and contracted, splitting into geometric shapes. Before erosion or new sediment filled them, the cracks hardened. Later, when more material covered them, the pattern was preserved. Now, when we split open the rock, we see the ancient surface perfectly intact, a snapshot of a drought that ended long before humans existed. Some of these rocks also show raindrop impressions, preserved moments when the first drops of a storm fell on dry mud. Together, these features tell stories of climate and weather from deep time. They reveal that the cycles of wet and dry, the rhythms of storm and drought, have played out across the planet for hundreds of millions of years. The oldest water on Earth has been trapped underground for billions of years. Deep within ancient rock formations, pockets of water have remained isolated from the surface for unfathomable lengths of time. In Canadian mines, scientists have discovered water that has been sealed away for more than 1 billion years, perhaps even 2 billion. This water is incredibly salty and contains dissolved gases from the early Earth. It has never seen sunlight, never evaporated into clouds, never flowed in a river. Despite its isolation, it supports microbial life, simple organisms that have adapted to exist in complete darkness, feeding on chemical energy from the rocks around them. Analyzing this ancient water provides clues about what the early Earth was like and how life might survive in extreme environments elsewhere in the solar system. To touch it is to touch a substance older than complex life, a liquid relic from an Earth so different it might as well be another world. Some minerals glow under ultraviolet light. In ordinary light, many minerals appear dull or unremarkable, but under ultraviolet illumination, they transform into glowing works of art. This property, called fluorescence, occurs when minerals absorb UV light and re-emit it as visible wavelengths. Calcite glows red or pink, willemite shines bright green, and scheelite radiates blue. Entire rock collections come alive under UV lamps, revealing hidden colors and patterns invisible to the naked eye. The phenomenon is caused by impurities or defects in the crystal structure that trap and release energy. Some minerals even continue to glow after the UV source is removed, a property called phosphorescence. Collectors seek out fluorescent specimens for their dramatic beauty, but the glow also serves scientific purposes. Geologists use UV light to identify minerals in the field and to trace ore deposits in mines. These glowing stones remind us that reality contains layers beyond what our eyes can see, hidden spectrums waiting to be revealed. The Earth's inner core is solid but surrounded by liquid. At the very center of our planet lies a sphere of solid iron and nickel, about the size of the moon. Despite temperatures exceeding 5,000 degrees Celsius, the core remains solid because of the immense pressure compressing it. Surrounding this inner core is the outer core, a sea of molten metal that flows and churns. The motion of this liquid iron generates Earth's magnetic field through a process called the geodynamo. As heat from the core escapes, it drives convection currents that create organized flows in the outer core. These flows of conducting fluid produce electrical currents, which, in turn, generate magnetic fields. The interaction between the solid inner core and the liquid outer core is complex and still not fully understood. The inner core may rotate slightly faster than the rest of the planet, and changes in its rotation rate might influence the magnetic field at the surface. Deep within the Earth, this hidden dynamo has been running for billions of years, protecting life from harmful cosmic radiation. Tectonic plates move at about the same rate your fingernails grow. The continents drift across the Earth's surface at roughly 3 to 5 centimeters per year. This is approximately the same speed at which human fingernails grow. The comparison makes the process feel more tangible, though the scales involved are vastly different. A fingernail grows and is trimmed away in weeks. A continent moves the same distance, but that movement accumulates over millions of years into thousands of kilometers. The Atlantic Ocean widens by a few centimeters annually as North America and Europe drift apart. The Pacific Plate slides northwest, carrying Hawaii slowly toward Alaska. These motions seem impossibly slow to us, yet they are fast enough to completely reconfigure the planet's surface over geological time. In 100 million years, the world map will be unrecognizable. Oceans will close, new mountains will rise, and continents will merge and split in patterns we can only imagine. Salt deposits mark the sites of ancient evaporated seas. Thick layers of salt buried beneath the ground tell stories of oceans that dried up millions of years ago. When a body of seawater becomes isolated from the larger ocean and evaporation exceeds inflow, the water grows saltier and saltier. Eventually, the dissolved minerals begin to crystallize and settle to the bottom. Over time, thick deposits of halite, gypsum, and other evaporate minerals accumulate. These layers can reach hundreds of meters in thickness, representing the complete evaporation of vast inland seas. Later, geological processes may bury these salt deposits under newer sediments. In some places, the salt flows slowly upward through overlying rock, forming domes that trap oil and gas. Salt mines operated today often excavate caverns in these ancient deposits, carving through minerals that once dissolved in primordial oceans. The salt we sprinkle on our food may have crystallized from seawater that vanished before the age of dinosaurs. Some beaches have sand made of tiny pieces of shells and coral. Not all sand is made of quartz ground from continental rocks. On tropical islands and coastlines, the beaches shimmer with white or pink sand composed almost entirely of broken shells, coral fragments, and the skeletons of marine organisms. Over time, waves pound these biological materials into fine particles that accumulate along the shore. Parrotfish contribute to this process by eating coral, and excreting fine sand. A single fish can produce hundreds of pounds of sand each year. The result is a beach, built not from eroded mountains, but from the remains of life itself. Walking on such a beach is like walking through the ruins of countless tiny ecosystems. Each grain was once part of something living, now transformed into a soft substrate that shifts with every tide. These biological beaches are vibrant, dynamic places where geology and biology blur together, creating landscapes of astonishing beauty. Permafrost contains frozen remnants of ancient ecosystems. In the Arctic, ground that has remained frozen for thousands of years preserves organic material in remarkable condition. Mammoth tusks, woolly rhinoceros remains, and entire preserved plants emerge from thawing permafrost. These frozen archives hold DNA, pollen, and seeds from ecosystems that vanished at the end of the last ice age. Scientists study permafrost cores to understand past climates and how ecosystems responded to warming. The organic matter trapped in permafrost also contains vast amounts of carbon. As global temperatures rise and permafrost thaws, this carbon is released as carbon dioxide and methane, amplifying warming in a feedback loop. The frozen ground is a library of the past and a warning about the future. Within its icy layers lie stories of mammoths grazing on tundra grasslands and ancient humans hunting in landscapes now buried beneath ice. Permafrost is geology's freezer, preserving history until warmth unlocks it once more. The Great Rift Valley is tearing Africa apart. Running for thousands of kilometers through East Africa, a great crack in the Earth's crust marks the slow splitting of the continent. Volcanic activity, earthquakes, and thinning crust reveal that a new ocean may eventually form there. The East African Rift is a divergent boundary where the Somali Plate is pulling away from the Nubian Plate. In a few tens of millions of years, the region that includes Ethiopia, Kenya, and Tanzania could separate from the rest of Africa, drifting eastward into its own landmass. Lakes such as Tanganyika and Malawi fill the rift's deep scars, early hints of the ocean that might someday flood in. Standing on the rift's edges is like witnessing the birth of a future continent. The process is slow beyond imagination, yet it is happening now beneath our feet, shaping the world of tomorrow. Geology does not pause. It simply continues, pulling continents apart, building mountains, and remaking the face of the earth. Petrified forests are trees turned to stone. In certain ancient landscapes, entire forests have been preserved as stone. When trees were buried rapidly by volcanic ash or sediment, minerals carried by groundwater seeped into the wood's cells. Over thousands of years, each tiny structure was replaced molecule by molecule with quartz, opal, or other minerals. The result is a fossil that still looks like wood, but feels cold and heavy to the touch. Sometimes trace elements color the stone in hues of red, yellow, or green, painting natural artwork within the grain. The petrified forest in Arizona contains logs scattered across a stark desert landscape, their insides revealing rings, knots, and bark texture in perfect detail. These trees grew during the Triassic period, more than 200 million years ago, in a world filled with early dinosaurs and giant amphibians. Now they lie as stone, monuments to the fact that nothing truly disappears. It only changes form, carrying the memory of life within crystalline permanence. Sinkholes form when underground caves collapse. Beneath many regions, especially those with the limestone bedrock, hidden cavities form as acidic water slowly dissolves the rock. Over time, these voids grow larger, creating underground rivers and caverns. When the roof of such a cavity becomes too thin to support the weight above, it collapses suddenly, creating a sinkhole. Some are only a few meters wide. Others stretch hundreds of meters across, swallowing cars, trees, and homes without warning. They form most often after heavy rain, when water seeps through cracks and weakens the layers below. Entire neighborhoods have been built atop such fragile foundations without realizing it. Scientists map vulnerable regions with radar and ground sensors to detect cavities before disaster strikes. Though dramatic, sinkholes are part of the planet's natural recycling of rock, where water patiently sculpts the landscape from beneath. Each collapse reveals the fragile balance between solid ground and the hidden hollows that lie quietly just below our everyday world. Banded iron formations are among the oldest rocks on Earth. Striped layers of red and gray rock, rich in iron, appear in ancient formations around the world. These banded iron formations date back more than 2 billion years and tell a remarkable story. When early cyanobacteria began producing oxygen through photosynthesis, the gas reacted with dissolved iron in the oceans. The iron oxidized and settled to the seafloor in layers, alternating with silica-rich sediments. Over millions of years, these layers compacted into rock, creating distinctive red and gray bands. Each stripe represents a cycle of oxygen production and iron precipitation. Today, these formations are mined for iron ore, the backbone of modern industry. Yet they began as the waste product of microscopic life. They mark one of the most important transitions in Earth's history, the moment when life began to change the chemistry of the entire planet. Every band is a heartbeat in the transformation from a world without breathable air to one where oxygen made complex life possible. Amber preserves ancient life in golden clarity. Tree resin, sticky and thick, sometimes trapped insects, spiders, and small creatures millions of years ago. Over time, the resin hardened and fossilized into amber, preserving its contents in three-dimensional perfection. Unlike other fossils that show only impressions or mineralized remains, amber captures soft tissues, delicate wings, and even pollen grains. Some specimens contain entire ecosystems, with multiple organisms frozen in a moment of interaction. Scientists have extracted DNA fragments from amber inclusions, though not enough to recreate extinct species as fiction imagines. The clarity of amber allows researchers to study anatomy in detail, revealing colors, structures, and behaviors of ancient life. Holding a piece of amber with an insect inside is like looking through a window into the past. The creature died tens of millions of years ago, yet it appears as if it could wake and fly away. Amber is time made solid, a golden preservation of moments that would otherwise have vanished completely. Stalactites and stalagmites grow so slowly, you cannot see them move. Inside limestone caves, dripping water carries dissolved minerals that slowly crystallize as it evaporates. From the ceiling, each droplet leaves behind a tiny ring of calcite that lengthens downward over centuries, forming a stalactite. Where the drops land, matching mounds grow upward as stalagmites. Eventually, they can meet to create towering columns. The process is so gradual that growth rates are measured in millimeters per century. Lantern light reveals their delicate textures, frozen waterfalls sculpted by time and patience. These formations are living records of the cave's history, recording changes in water chemistry and climate. When viewed together, they resemble forests of stone, where every branch and trunk was born from a single droplet that fell through darkness. Walking through a cavern filled with these structures is like entering a slow-motion clock where time moves at the pace of minerals crystallizing, building beauty through persistence beyond human measure. The youngest ocean floor is only about 200 million years old. While the continents contain rocks billions of years old, the seafloor is surprisingly young. Along mid-ocean ridges, molten rock rises, cools, and forms new crust that slowly spreads outward. As it drifts, it eventually sinks back into the mantle at deep ocean trenches, where one plate slides beneath another. This recycling means no ocean crust lasts longer than about 200 million years, a fleeting moment in Earth's long history. The continents, by contrast, are ancient survivors that have floated above the cycle of destruction. If you could watch the planet's surface over time, you would see the oceans form and vanish like the rhythm of breath. The seafloor is the planet's heartbeat, renewing itself endlessly. A reminder that even the deepest, darkest places on Earth are alive with motion and change. Certain clays expand when wet and shrink when dry. Bentonite and other smectite clays have a unique property. They can absorb water into their crystal structure, causing them to swell dramatically. When they dry out, they contract again. This cycle creates problems for construction because foundations built on these soils can shift and crack as moisture levels change with seasons. Yet, the same property makes these clays useful. They seal ponds and wells, stopping water from seeping away. They are used in drilling mud to lubricate drill bits and carry rock chips to the surface. Ancient peoples used them for pottery and medicine. The expansion occurs because water molecules fit between the layers of the clay's crystalline structure, pushing them apart. When the water evaporates, the layers collapse back together. This simple mechanism has profound effects on landscapes, engineering, and industry. It shows how the molecular structure of minerals determines not just their appearance, but their behavior and usefulness. Rivers of stone once flowed beneath ancient volcanoes. Lava tubes form when the surface of a lava flow cools and hardens, while molten rock continues to flow beneath. When the eruption ends and the lava drains away, hollow tunnels remain, sometimes stretching for kilometers underground. These tubes can be large enough to walk through, their walls smooth and glassy from the heat of passing magma. In Hawaii, Iceland, and the Pacific Northwest, lava tubes create networks of caves that preserve the internal structure of ancient flows. Some contain formations where lava dripped from the ceiling like molten stalactites before freezing in place. Others show high water marks on the walls, indicating the depth of flowing lava. Exploring a lava tube is like walking through the veins of a volcano, seeing the pathways that once carried fire from deep chambers to the surface. They remind us that even solid rock was once liquid, flowing with currents and eddies before cooling into the stillness we see today. Opal forms in the shapes of replaced fossils. Sometimes groundwater rich in silica seeps through the remains of shells, bones, or wood buried in sediment. The original material slowly dissolves away as opal precipitates in its place, molecule by molecule. The result is a fossil made entirely of shimmering opal, preserving the original shape in translucent, colorful stone. Australia is famous for opalized fossils, including shells, plants, and even dinosaur bones replaced with precious opal. These fossils glow with internal fire, their surfaces playing with light in rainbow patterns. Collectors prize them for their beauty and rarity. Each one represents a perfect alignment of circumstances where the right minerals, in the right concentration, replaced organic material before it decayed. The fossil becomes a ghostly echo of life, transmuted into gem. To hold an opalized shell is to hold both death and transformation, an object that is simultaneously fossil and treasure, memory and art. Some mountains are made of uplifted seafloor. The highest peaks on Earth, including Mount Everest, contain limestone layers filled with marine fossils. This rock formed on the bottom of an ancient ocean called the Tethys Sea, more than 50 million years ago. When the Indian Plate collided with the Eurasian Plate, the seafloor between them was crumpled and thrust upward, carrying ocean sediments to the roof of the world. Climbers ascending Everest walk past rocks that once lay beneath waves, their surfaces still embedded with shells and coral. The journey from seafloor to summit took millions of years of continuous uplift, grain by grain and meter by meter. These marine fossils at extreme altitude are proof of the planet's immense power to reshape itself. What was once the domain of fish and plankton now towers in thin air above the clouds. Mountains remember their origins, carrying the ocean with them as they rise. Glaciers can contain ice that is hundreds of thousands of years old. Deep within the thick ice of Antarctica and Greenland lie layers that accumulated during ancient ice ages. Scientists drill cores through this ice, extracting cylinders that reveal climate history, stretching back nearly 1 million years. Each layer contains trapped air bubbles, tiny samples of the atmosphere from the year the snow fell. By analyzing these bubbles, researchers can measure past levels of carbon dioxide, methane, and temperature. Dust particles within the ice tell of volcanic eruptions and desert storms. Pollen grains reveal what plants grew nearby. The deepest ice is under such pressure that it behaves more like rock than frozen water, deforming slowly under its own weight. To study glacier ice is to read a detailed diary of Earth's climate, written year by year in layers of compacted snow. Each core sample is a window into the past, showing how the planet has breathed and changed across hundreds of millennia. Earthquakes travel through the Earth as waves. When rock suddenly breaks or shifts along a fault, it releases energy that radiates outward as seismic waves. These waves travel through solid rock, liquid metal, and everything in between. There are several types. P waves, or primary waves, compress and expand material like sound waves and move fastest. S waves, or secondary waves, shear material from side to side and cannot travel through liquid. Surface waves roll along the crust like ripples on water, causing most of the shaking we feel. By studying how these waves travel, scientists can map the interior of the Earth. S waves stop at the outer core boundary, proving it is liquid. P waves bend as they pass through different layers, revealing changes in density and composition. Every earthquake, no matter how destructive, provides data that helps us understand the hidden structure of our planet. The waves carry information from depths we can never visit directly. Hot springs are heated by geothermal energy from below. In volcanic regions and along tectonic boundaries, groundwater seeps deep into the crust where it encounters hot rock or magma. The water heats up, sometimes to boiling or beyond, and rises back to the surface through cracks and fissures. When it emerges, it creates hot springs, geysers, and fumaroles. The water often carries dissolved minerals that precipitate around the vents, building colorful terraces of travertine or silica. Microorganisms thrive in these hot, mineral-rich waters, forming mats of brilliant orange, green, and yellow. Some of these microbes are among the most heat-tolerant life forms known, surviving in water hot enough to scald skin. Hot springs have been used for bathing and healing for thousands of years. The heat rising from within the Earth reminds us that the planet is not a cold, dead sphere, but a warm, active body that releases its internal energy in countless places across its surface. Coal swamps covered vast areas during the Carboniferous period. Around 300 million years ago, much of the Earth's land was covered with dense tropical swamps. Giant ferns, club mosses, and primitive trees grew in the thick forests that could reach 40 meters tall. When these plants died, they fell into oxygen-poor water where decay was slow and incomplete. Layer upon layer of plant material accumulated, building thick deposits of peat. Over time, heat and pressure transformed the peat into coal, locking away carbon that had been pulled from the atmosphere. The amount of plant material buried during this period was so vast that it noticeably reduced atmospheric carbon dioxide levels. The coal we mine today is the compressed remains of those ancient forests, energy stored from sunlight that fell on leaves hundreds of millions of years ago. Burning, it releases that ancient carbon back into the air, reversing in centuries what took millions of years to bury. Concretions are natural cement balls formed in sediment. Sometimes minerals precipitate around a nucleus, such as a shell, bone, or plant fragment buried in sediment. As mineral-rich water flows through the surrounding material, it deposits layer after layer around the object. Over time, this creates a hard, spherical or disc-shaped mass called a concretion. They can range from pebble size to several meters across. When erosion removes the softer surrounding sediment, concretions remain as strange, smooth stones scattered across beaches and badlands. Some concretions are hollow, with crystals lining the interior. Others preserve fossils in their centers, the original nucleus around which the formation grew. These natural sculptures form through chemical processes that concentrate minerals in localized areas. They appear mysterious and deliberate, as though shaped by hands. But they are entirely the work of groundwater and chemistry, building spheres of stone through patience and precipitation. Iron meteorites are fragments of ancient planetary cores. When small planets and large asteroids formed in the early solar system, the heaviest metals sank to their centers, creating iron-nickel cores. Later, collisions shattered some of these bodies, scattering fragments through space. The iron meteorites that fall to Earth today are pieces of those destroyed cores, material that once lay at the heart of worlds that no longer exist. When cut and polished, they reveal beautiful crystalline patterns called Widmanstätten patterns, formed as the metal cooled incredibly slowly over millions of years in space. These patterns cannot be reproduced artificially because they require cooling rates measured in degrees per million years. Holding an iron meteorite is holding the core of a vanished planet, a world that formed, differentiated, and was destroyed before Earth finished growing. They are orphaned fragments, the last remains of planetary bodies that met violent ends in the chaos of the young solar system. Basalt columns form when lava cools and contracts. When thick lava flows cool, they often crack into geometric columns with 5 or 6 sides. This happens because the cooling rock contracts uniformly, and the most efficient way to relieve the stress is to form a network of polygonal fractures. The columns can be remarkably regular, creating structures that look almost artificial. The Giant's Causeway in Northern Ireland and Devil's Post Pile in California are famous examples. These hexagonal pillars stack like bundles of pencils, their flat tops creating stepping stones across ancient lava flows. The size of the columns depends on how quickly the lava cooled. Faster cooling produces smaller columns, while slower cooling allows larger ones to form. Walking among basalt columns is like exploring a natural cathedral, where geometry and geology merge into architecture built by cooling rock. They stand as proof that nature follows mathematical rules, creating order from the simple physics of contraction. Desert varnish is a dark coating formed by microbes and minerals. In arid regions, many rocks are covered with a thin, dark layer that looks like paint or glaze. This desert varnish forms over thousands of years as dust settles on rock surfaces and microorganisms metabolize manganese and iron from the particles. The microbes concentrate these metals, creating a patina that ranges from brown to black. Ancient peoples carved petroglyphs through this varnish, exposing lighter rock beneath to create images that have lasted for millennia. The varnish protects the underlying stone from erosion and weathers slowly, preserving the carvings. Scientists study desert varnish to understand past climates because its formation rate changes with moisture and temperature. Some varnish may be tens of thousands of years old, a slow accumulation of minerals and microbial activity that turns bare rock into a darkly shining surface, a collaboration between life and geology that paints the desert stones. Meteorite impacts can create shocked quartz. When an asteroid or comet strikes the Earth at tremendous speed, the impact generates pressures far beyond anything produced by normal geological processes. These extreme forces create unique changes in minerals. Quartz crystals subjected to shock develop sets of parallel fractures and deformation patterns called planar deformation features. These microscopic structures can only form under the intense pressures of impact or nuclear explosions. Geologists use shocked quartz as a diagnostic tool to identify ancient impact sites that are otherwise eroded beyond recognition. The discovery of shocked quartz in the rock layer marking the end of the Cretaceous period helped confirm that an asteroid impact contributed to the mass extinction that killed the dinosaurs. Each grain of shocked quartz is a fossil of violence, a mineral that experienced forces powerful enough to rearrange its atomic structure in fractions of a second. The moho is the boundary between crust and mantle. Beneath the continents and oceans lies an invisible boundary, where the composition of rock changes dramatically. This transition zone, called the Mohorovičić discontinuity, or MOHO, marks where the crust ends and the mantle begins. It sits about 30 to 50 kilometers deep under continents, but only 5 to 10 kilometers beneath the ocean floor. Above it, rock is cooler and more varied in composition. Below it, the mantle consists of denser, iron-rich rock that extends thousands of kilometers downward. Seismic waves change speed when they cross the moho, which is how scientists discovered and map it. No one has ever drilled through the moho, though several projects have tried. It remains one of the boundaries we know exists, but have never directly sampled. The moho separates the thin skin we inhabit from the vast bulk of rock beneath, a frontier between the familiar crust and the mysterious depths below. Subduction zones are where oceanic crust returns to the mantle. When two tectonic plates converge and one is denser than the other, the denser plate bends and slides beneath. This process, called subduction, carries seafloor back into the mantle where it melts and is recycled. Subduction zones are marked by deep ocean trenches, the lowest points on Earth's surface. They are also sites of intense geological activity. As the descending plate heats up and releases water, it triggers melting in the overlying mantle. This magma rises to form volcanic arcs, chains of volcanoes parallel to the trench. Subduction zones produce the planet's most powerful earthquakes, as enormous slabs of rock grind past each other. The process is essential to plate tectonics, providing a way for old crust to be destroyed as new crust forms at mid-ocean ridges. Without subduction, the Earth's surface would be static, locked in place, unable to renew itself. Pillow lava forms when magma erupts underwater. When molten rock emerges beneath the ocean, it cools so rapidly that its outer layer solidifies almost instantly while the interior remains liquid. Continued flow causes the hardened crust to bulge and break, forming rounded, pillow-shaped blobs that stack upon each other. Each pillow is a snapshot of flow frozen in an instant, showing how magma interacts with cold seawater. These formations cover vast areas of the seafloor along mid-ocean ridges. When geologists find pillow lava on land, it tells them the area was once submerged beneath deep water. The shapes are distinctive and beautiful, like stone balloons or giant cushions piled in heaps. Their surfaces often show glassy textures where the lava chilled instantaneously. Pillow lavas are geological sculptures, proof that even in the crushing depths of the ocean, volcanic forces create and shape new crust in patterns both chaotic and strangely organic. Cave pearls form in underground pools. In some caves, dripping water creates small, spherical stones called cave pearls. They form when calcium carbonate precipitates around a tiny nucleus, such as a sand grain in a shallow pool. Water dripping into the pool keeps the pearl in motion, ensuring even coating on all sides. Over hundreds or thousands of years, the pearl grows layer by layer, becoming smooth and round. Some are the size of peas, others as large as marbles. When removed from the water, they stop growing and become fossils of the cave's hydrological history. Their layers, like tree rings, record variations in water chemistry and flow over time. Cave pearls often accumulate in natural basins or depressions, nestled together like eggs in a nest. Finding them is like discovering hidden treasure, perfectly round stones crafted by nothing but dripping water and the slow accumulation of minerals in darkness. Permineralization preserves ancient wood in perfect detail. When wood is buried quickly and groundwater flows through it, minerals dissolved in the water can infiltrate the cellular structure. Over time, these minerals precipitate within the cells, filling voids and coating surfaces. The wood's original organic material may remain, or it may be completely replaced. But either way, the structure is preserved in three-dimensional detail. Unlike petrified wood, where the material is entirely replaced by stone, permineralized wood retains some organic compounds. Scientists can sometimes study the cell structure under microscopes, seeing individual cells, growth rings, and even evidence of ancient diseases or insect damage. The colors in permineralized wood come from different minerals. Iron creates reds and oranges. Copper produces greens and blues. Manganese gives purples and blacks. Each piece is a collaboration between biology and geology. Ancient life transformed into something that is neither quite wood nor quite stone. The Appalachian and Atlas Mountains were once connected. Long before the Atlantic Ocean existed, the eastern edge of North America was joined to northwestern Africa. When these continents collided to form the supercontinent Pangaea, The impact crumpled the crust and raised a massive mountain range. Over time, erosion wore these mountains down. Then, around 200 million years ago, the continents began to split apart, and the Atlantic opened between them. The mountain chain was divided, leaving the Appalachians in North America and the Atlas Mountains in Africa. Despite being separated by an ocean, these ranges share similar rock types, ages, and structures. They are mirror images, two halves of what was once a single mountain system. Standing in either range is standing in a landscape that remembers a time when all the continents were one, when you could have walked from North America to Africa without crossing water. Geothermal vents power unique ecosystems without sunlight. On the deep ocean floor, where tectonic plates pull apart, seawater seeps into cracks and is heated by magma below. It rises back up through hydrothermal vents, carrying dissolved minerals and chemicals. Around these vents, life thrives in complete darkness. Bacteria use the chemical energy from hydrogen sulfide and methane to produce food through chemosynthesis. These bacteria form the base of a food web that includes giant tube worms, clams, crabs, and fish, all adapted to extreme conditions. Temperatures can swing from near freezing to over 400 degrees within meters. Yet life not only survives, but thrives. The discovery of these ecosystems in the 1970s revolutionized biology, proving that life does not require sunlight. It only needs energy and water. These vent communities may resemble the earliest ecosystems on Earth and could exist on other worlds with subsurface oceans. Sand dunes can reach heights taller than skyscrapers. In some of the world's great deserts, sand accumulates into dunes that tower hundreds of meters above the surrounding landscape. The tallest dunes in the world, found in Namibia and Algeria, rise more than 300 meters from base to crest. These massive structures form when strong, consistent winds transport sand and deposit it in areas where wind speed decreases. The windward side of a dune has a gentle slope where sand grains creep upward. The leeward side is steeper, where sand avalanches down after being blown over the crest. Dunes migrate slowly across the desert as wind continually removes sand from one side and deposits it on the other. Some dunes travel several meters per year, burying everything in their path. Despite their movement, the largest dunes have existed for thousands of years, slowly marching across the landscape. They are mountains of sand, temporary sculptures that shift and breathe with the wind. Erosion shapes rocks into natural arches and bridges. In regions with layered sedimentary rock, erosion sometimes creates stunning natural arches. Water, wind, and ice exploit weaknesses in the rock, carving away softer layers while harder layers resist. Over thousands of years, this differential erosion can hollow out openings, leaving bridges of solid stone spanning gaps. Arches National Park in Utah contains more than 2,000 natural arches, each one a unique sculpture in red sandstone. Some span hundreds of feet, delicate ribbons of rock defying gravity. Eventually, all arches collapse as erosion continues to weaken them. The lifespan of an arch can be tens of thousands of years, but it is always temporary. New arches form as old ones fall, part of the continuous process of landscape evolution. To stand beneath a natural arch is to witness a fleeting moment in geological time, a structure that will exist for millennia, yet is fundamentally impermanent. Radiometric dating measures the age of rocks using atomic decay. Certain elements are naturally radioactive, meaning their atoms decay into different elements at predictable rates. By measuring the ratio of parent atoms to daughter atoms in a rock sample, scientists can calculate how long ago the rock formed. Different isotopes decay at different rates, allowing geologists to date rocks from thousands to billions of years old. Carbon-14 decays quickly and is used for organic materials up to about 50,000 years old. Uranium-lead dating works on much older rocks, extending back to the formation of the Earth. Radiometric dating revolutionized geology by providing absolute ages rather than relative sequences. It confirmed that the Earth is about 4.5 billion years old and allowed scientists to construct a detailed timeline of geological and biological history. The technique relies on the constancy of radioactive decay, one of the most reliable processes in nature, a clock that has been ticking since the atoms themselves were forged in stars. The Himalayas continue to rise even as erosion wears them down. The collision between the Indian and Eurasian plates that began 50 million years ago continues today. The Himalayas gain a few millimeters of height each year as the plates push together. At the same time, glaciers carve valleys, rivers cut gorges, and landslides strip away rock. The mountains are engaged in a constant battle between tectonic uplift and erosional destruction. In some areas, uplift wins and peaks grow taller. In others, erosion dominates and summits shrink. The balance shifts over time and across regions. Deep earthquakes regularly shake the range, evidence of ongoing collision. GPS measurements track the motion with precision, showing that the process that built these giants is not finished. The mountains breathe with geological life, rising and falling in a slow rhythm that will continue for millions of years, until the tectonic forces driving them finally ease. Certain minerals are harder than steel. The Mohs hardness scale ranks minerals from 1 to 10 based on their ability to scratch each other. Diamond, at 10, is the hardest natural substance known. It can scratch or cut nearly anything, including steel, which ranks around 5 to 6. Corundum, which includes ruby and sapphire, ranks 9 and is also harder than steel. These extreme hardnesses result from the strong chemical bonds within their crystal structures. Diamond's carbon atoms are arranged in a rigid three-dimensional lattice that resists deformation. This property makes these minerals valuable not just as gemstones, but as industrial tools for cutting, grinding, and drilling. Diamond-tipped drill bits bore through solid rock. Corundum powder polishes metal and glass. The hardness of minerals is a fundamental property that affects how they form, survive, and are used. It is a reminder that some arrangements of atoms create structures so strong that almost nothing can break them. Tsunamis are triggered by underwater earthquakes and landslides. When an earthquake occurs beneath the ocean and causes vertical displacement of the seafloor, it pushes or pulls the entire water column above it. This creates waves that spread outward in all directions. In deep water, tsunami waves travel fast, but have low heights, often less than a meter. They can cross entire oceans in hours, barely noticeable to ships. But as they approach shallow coastal waters, they slow down and grow taller. The wave energy compresses into a smaller volume, and the water can rise tens of meters above normal sea level. Tsunamis differ from regular waves because they involve the movement of the entire water column, not just the surface. Their wavelengths can be hundreds of kilometers, meaning the water keeps rising for minutes. Understanding tsunamis requires understanding both the geology that triggers them and the physics of how waves propagate through water. Granite forms deep underground and cools very slowly. unlike volcanic rocks that solidify quickly at the surface, granite crystallizes from magma trapped far below in large chambers. The slow cooling allows large visible crystals of quartz, feldspar, and mica to grow over thousands or millions of years. The resulting rock has a coarse, speckled appearance with interlocking crystals. Granite is extremely hard and resistant to erosion, which is why it forms the cores of many mountain ranges and ancient continental shields. When erosion removes the overlying rock, granite is exposed at the surface. Its durability makes it a favored building stone, used in monuments and countertops. The granite cliffs of Yosemite and the massive domes of the Sierra Nevada are examples of these deep-borne rocks revealed by millions of years of erosion. Each grain of granite is a crystal that grew in darkness and heat, slowly arranging itself into the familiar pattern we see when the rock finally emerges into daylight. Meandering rivers constantly change their paths. Rivers flowing across flat terrain naturally develop curves and bends called meanders. The water moves faster on the outside of each curve, eroding the bank. On the inside, it moves slower and deposits sediment. Over time, this causes the meander to migrate sideways, creating a shifting path across the floodplain. Sometimes, a river meander becomes so curved that the river cuts through the narrow neck of land, abandoning the old loop. The abandoned curve becomes an oxbow lake, a crescent-shaped body of water isolated from the main channel. Over hundreds or thousands of years, a meandering river can completely rework the landscape, leaving behind a maze of old channels, lakes, and sediment deposits. The river's current path is only the latest in a long history of wandering. Meandering is natural and inevitable for low-gradient rivers, a beautiful expression of how flowing water seeks equilibrium with the land. Soil takes thousands of years to form from bare rock. The thin layer of soil that supports nearly all terrestrial life forms incredibly slowly. It begins when bare rock is exposed to weathering. Water seeps into cracks and freezes, wedging the rock apart. Acids from rain and organic matter dissolve minerals. Lichens and mosses colonize the surface, producing more acids and trapping moisture. Over centuries, a thin layer of broken rock and organic material accumulates. Plants take root, their roots further breaking the rock. Animals burrow and mix the material. Bacteria and fungi decompose organic matter, enriching the soil. A single centimeter of soil can take decades or centuries to form, depending on climate and rock type. A rich agricultural soil might represent thousands of years of development. This is why soil erosion is so concerning. What takes millennia to build can wash away in a single storm. Soil is not just dirt. It is a living, dynamic system, and one of the planet's most precious resources. The oldest evidence of life is preserved in ancient rocks. In some of the Earth's oldest surviving rocks, dating back more than 3.5 billion years, scientists have found structures and chemical signatures consistent with microbial life. Stromatolites, layered structures built by bacterial mats, appear in rocks from Australia and southern Africa. Carbon isotope ratios in these ancient rocks suggest biological processing. While direct fossils of individual cells are vanishingly rare and controversial, the evidence points to life existing very early in Earth's history. These primitive microbes lived in a world with no oxygen, no ozone layer, and likely frequent asteroid impacts. They survived by metabolizing chemicals from their environment, living in shallow water or around hydrothermal vents. Their existence set the stage for everything that followed. beginning the slow transformation of the planet from a barren world to one teeming with life. The rocks that preserve their traces are among our most precious scientific treasures. Tectonic plates sometimes get stuck and then suddenly slip. Along fault lines, tectonic plates are always trying to move past each other. Friction holds them in place, and stress builds up over years, decades, or centuries. The rock deforms elastically, storing energy like a compressed spring. Eventually, the stress exceeds the strength of the rock, and it fails suddenly. The plates slip, releasing the stored energy as an earthquake. This is called stick-slip behavior, and is the reason most earthquakes occur in sudden jerks rather than smooth sliding. The longer the plates remain locked, the larger the eventual earthquake. Seismologists study these locked zones, trying to estimate when and where the next rupture will occur. After the earthquake, the cycle begins again as the plates resume their slow motion and stress rebuilds. This pattern has repeated countless times throughout Earth's history, the planet's way of accommodating motion that cannot occur smoothly. Fossilized footprints reveal how ancient animals moved. When animals walked across soft mud or sand and their tracks were quickly buried and hardened, those footprints could be preserved as fossils. These trace fossils provide information that body fossils cannot. They show how the animal stood and moved, whether it walked on 2 legs or 4, whether it dragged its tail or held it aloft. Trackways, multiple footprints in sequence, reveal speed and behavior. Some show evidence of herding, with many individuals moving together. Others capture interactions, like a predator following prey. Dinosaur footprints have been found on every continent, preserving moments from their daily lives. Human footprints, dating back thousands of years, tell stories of ancient migrations and activities. Unlike bones, which show what an animal was built like, footprints show what it actually did. Each one is a snapshot of motion, a brief journey turned eternal in stone. The Grand Canyon exposes nearly 2 billion years of Earth history. As you descend into the canyon, you walk backward through time. The youngest rocks at the rim are about 270 million years old. As you descend, each layer is progressively older. Near the bottom, the inner gorge contains metamorphic rocks nearly 2 billion years old, among the oldest on Earth. Between these layers, entire chapters of history are missing. Gaps where erosion removed rock before new layers were deposited. These gaps, called unconformities, represent millions or even hundreds of millions of missing years. The canyon is a vertical textbook of geology, its walls displaying desert dunes turned to stone, ancient seafloors, river deposits, and volcanic intrusions. Reading the layers requires understanding not just what is there, but also what is missing. The canyon tells a story of seas advancing and retreating, mountains rising and eroding, climates shifting from tropical to arid and back again. Clastic sedimentary rocks are made from fragments of other rocks. The term clastic means broken, and these rocks form from pieces of pre-existing rock that have been weathered, transported, and deposited. Sand becomes sandstone, mud becomes shale, and gravel becomes conglomerate. The size of the fragments tells geologists about the energy of the environment where they were deposited. Large cobbles require fast-moving water, like rivers or beaches with strong waves. Fine mud settles only in still water, like deep lakes or calm ocean floors. The spaces between grains can fill with minerals that cement them together, turning loose sediment into solid rock. Clastic rocks are the most common sedimentary rocks and contain most of the world's fossils. They are records of erosion and deposition, of landscapes being torn down in one place and rebuilt in another. Every sandstone cliff was once a beach or desert. Every shale was once mud at the bottom of a sea. Calcite fizzes when it comes in contact with acid. One of the simplest and most reliable tests in geology involves placing a drop of dilute hydrochloric acid on a rock. If the rock contains calcite, it fizzes and bubbles vigorously as carbon dioxide gas is released. This reaction distinguishes limestone and marble from similar-looking rocks. The fizz test works because calcite, calcium carbonate, reacts with acid to form calcium chloride, water, and carbon dioxide. The bubbles are the carbon dioxide escaping. Even weak acids like vinegar produce a reaction, though less dramatically. Geologists have used this test in the field for over a century because it is fast, simple, and reliable. The reaction is also why limestone dissolves in rainwater, which is slightly acidic. Over thousands of years, this process carves caves, creates sinkholes, and sculpts landscapes in regions with carbonate rocks. Volcanic ash can circle the globe and affect climate. When volcanoes erupt explosively, they inject ash and sulfur dioxide high into the stratosphere. There, the particles can remain for months or years, spread by high-altitude winds until they encircle the planet. These particles reflect sunlight back into space, cooling the surface below. Major eruptions have caused noticeable climate effects. The eruption of Mount Tambora in Indonesia in 1815 created the year without a summer, when snow fell in June in New England and crops failed across Europe. More recently, Mount Pinatubo's eruption in 1991 lowered global temperatures by about half a degree for 2 years. The ash eventually settles out, but while airborne, it creates spectacular sunsets and subtle cooling. Volcanic eruptions remind us that the planet's internal processes can influence its external climate, that rock and fire can change weather patterns and growing seasons across the entire world. Desert roses are crystals shaped like flower petals. In arid regions where groundwater evaporates from sand, dissolved minerals can crystallize in unusual forms. Gypsum or barite sometimes grows in rosette shapes, with thin, flat crystals radiating from a center like flower petals. These formations, called desert roses, can be stunningly beautiful, their surfaces dusted with sand grains trapped during growth. They form just below the surface as capillary action draws mineral-rich water upward. As the water evaporates, minerals precipitate, building the crystals outward in all directions. Some desert roses are small enough to hold in your palm. Others weigh hundreds of pounds. Collectors prize them for their organic appearance, the way mineral geometry mimics biological form. They are reminders that the same forces that build crystals can, under the right conditions, create shapes that look almost alive. The oldest fossils of multicellular life are more than 600 million years old. For billions of years, life on Earth consisted only of single-celled organisms. Then, during a period called the Ediacaran, complex multicellular creatures appeared. These early animals had soft bodies and no hard parts like shells or bones. Their fossils appear as impressions in fine-grained sediment, ghost-like outlines of frond-shaped, disc-shaped, and segmented forms. Many look unlike any animal alive today, leading to debates about what they were and how they relate to modern life. Some may be early relatives of animals we know. Others might represent entirely extinct evolutionary experiments. Their sudden appearance and diversity suggest a major transition in the history of life, when cells learned to cooperate in building large, complex bodies. The Ediacaran fossils are windows into this mysterious time, showing us a world on the cusp of the explosion of diversity that would follow in the Cambrian period. Quartz is one of the most abundant and stable minerals on Earth. Silicon and oxygen, the two most common elements in the Earth's crust, combine to form quartz. It appears in granite, sandstone, quartzite, and many other rocks. Quartz is hard, resistant to weathering, and chemically stable. When rocks break down, quartz grains often survive as sand while other minerals dissolve or alter. This is why so many beaches and deserts consist primarily of quartz sand. The mineral forms beautiful crystals, sometimes clear as glass, other times colored by trace impurities into varieties like amethyst, citrine, and rose quartz. It has practical uses too. Its hardness makes it suitable for cutting tools and abrasives. Its piezoelectric properties allow it to generate electric charge under mechanical stress, making it useful in electronics. Quartz is so common and essential that it threads through nearly every aspect of geology and human industry, a mineral that is simultaneously ordinary and extraordinary. Weathering and erosion are different processes. Weathering breaks rock down into smaller pieces or changes its chemical composition, but the material stays in place. Physical weathering happens when rocks crack due to freezing water, plant roots, or temperature changes. Chemical weathering occurs when minerals react with water, oxygen, or acids, forming new minerals or dissolving entirely. Erosion, on the other hand, is the transportation of weathered material by wind, water, ice, or gravity. A rock can weather for thousands of years without eroding if nothing moves the fragments away. Conversely, erosion requires weathering to provide the material to transport. Together, these processes reshape landscapes, wearing down mountains and filling valleys. They work slowly but relentlessly, grain by grain, transforming solid rock into sediment that travels from highlands to lowlands, from continents to oceans, in a cycle that has continued for billions of years. Folded rock layers show the immense forces within the Earth. In many mountain ranges, you can see rock layers that are no longer horizontal, but bent into curves, waves, and even complete loops. These folds formed when tectonic forces compressed the rock with such strength that solid layers buckled like fabric. Imagine the force required to bend rock that seems utterly rigid. It happens at depths where heat and pressure make rock slightly plastic, able to deform without breaking. The result is spectacular. Anticlines arch upward, synclines dip downward, and sometimes the folding is so intense that layers are overturned or stacked on top of each other. Geologists study these structures to understand the history of tectonic collisions. Each fold is a record of continental drift, of the slow, powerful forces that can take flat layers of sediment and turn them into the complex architecture of mountain ranges. Geyserites are mineral deposits from geysers. Around geysers and hot springs, dissolved silica precipitates from the cooling water, building terraces, mounds, and delicate formations. These structures, called geyserites or sinter, preserve the plumbing of the hydrothermal system. The deposits can contain fossils of microorganisms that lived in the hot water, including some of the most heat-tolerant life forms on Earth. Ancient geyserites are found in rocks around the world, evidence of past geothermal activity. Studying them helps scientists understand where hot springs once existed and what conditions prevailed. Geyserites also provide analogs for searching for life on other planets. If microbes can thrive in boiling water and leave traces in mineral deposits, similar processes might occur on Mars or icy moons with subsurface oceans. Every geyser is a living laboratory of chemistry and biology, building structures that will outlast the system that created them. Certain bacteria can survive extreme conditions in rock. Deep within the Earth's crust, in fractures filled with water, bacteria have been found living kilometers below the surface. These extremophiles survive on chemical energy, metabolizing hydrogen, sulfur, or iron compounds. They exist in complete darkness, under immense pressure, and sometimes at temperatures above 100 degrees Celsius. Some may divide only once per decade or century, living life in extreme slow motion. These discoveries challenge our understanding of where life can exist. If microbes thrive deep in rock, far from sunlight and photosynthesis, similar life might exist on Mars or in the icy crusts of Europa and Enceladus. The deep biosphere may contain more biomass than all surface life combined. A hidden kingdom of microbes that has been living beneath our feet since the planet cooled enough to allow liquid water in fractured stone. Glacial erratics are boulders carried far from their origin. Scattered across landscapes far from any mountains, enormous boulders sometimes sit in fields or on hillsides, completely different in composition from the local bedrock. These glacial erratics were plucked from distant locations by moving ice sheets and carried hundreds or even thousands of kilometers before being deposited when the ice melted. Some erratics weigh thousands of tons, massive monuments to the power of ice. Before geologists understood glaciation, these displaced boulders puzzled observers who could not imagine how they arrived. Some cultures attributed them to giants or divine intervention. Now we know they are geological travelers, rocks that rode rivers of ice across continents during the ice ages. Each erratic can be traced back to its source by matching its composition to distant rock formations, mapping the paths of long-vanished glaciers. Minerals form in specific temperature and pressure conditions. Each mineral has a stability field, a range of conditions where it forms and remains stable. When conditions change, minerals can transform into different forms or break down entirely. This is why geologists can use the minerals in a rock to determine the conditions under which it formed. The presence of certain minerals indicates specific depths, temperatures, or chemical environments. For example, diamonds form only at extreme pressures deep in the mantle. Zeolites form in volcanic rocks altered by low-temperature water. By mapping mineral assemblages, scientists can reconstruct the history of a rock, determining how deep it was buried, how hot it became, and whether it was exposed to fluids. Minerals are geological thermometers and barometers, recording the conditions of their formation in their crystal structures. They allow us to read the invisible history of pressure and heat written into stone. Ripple marks in sandstone preserve ancient water currents. On the surfaces of some sedimentary rocks, you can see patterns of parallel ridges and troughs that look like ripples in sand. These are fossilized ripple marks, formed when currents of water or wind moved sediment into regular patterns. The shape and spacing of the ripples indicate the strength and direction of the current. Symmetrical ripples form under oscillating waves. Asymmetrical ripples indicate a current flowing in one direction. When sediment buried these ripples quickly, they hardened into rock, preserving the pattern. Now, hundreds of millions of years later, we can look at them and know which way the water flowed in an ancient stream or the direction waves moved across a prehistoric beach. These features are time capsules of fluid dynamics, frozen moments of motion preserved in stone, allowing us to reconstruct vanished rivers, lakes, and shorelines from deep time. The crystalline structure of minerals determines their properties. Every mineral has a specific arrangement of atoms that repeats in 3 dimensions. This crystal structure determines the mineral's hardness, cleavage, color, and many other properties. Diamond and graphite are both pure carbon, but diamond's atoms are arranged in a strong 3-dimensional network, while graphite's atoms form weak layers that slide past each other easily. This difference in structure makes diamond the hardest natural substance, while graphite is soft enough to write with. Similarly, the way atoms arrange themselves determines how a mineral breaks. Some shatter randomly, others split along flat planes called cleavage surfaces. Crystal structure also influences how minerals interact with light, creating the colors and optical properties we see. Understanding crystal structure is fundamental to understanding why minerals behave as they do, why some are hard and others soft, why some are transparent and others opaque. Varves are annual layers in lake sediments. In some lakes, especially those fed by glacial meltwater, sediments settle in distinct seasonal layers. During summer, when melt rates are high, coarser particles settle out. In winter, only the finest clay settles through the still water. The result is a couplet of layers, one light and coarse, one dark and fine. Each couplet represents a single year, like a tree ring. These annual layers, called varves, can be counted to determine the age of the sediment and to study past climate. Thick summer layers indicate years with warm weather and heavy melting. Thin layers suggest cooler conditions. By counting and measuring varves, scientists can reconstruct climate records going back tens of thousands of years. Some varve sequences preserve evidence of volcanic eruptions, floods, and other events. They are calendars written in sediment, recording the passage of years at the bottom of ancient lakes. Tektites are natural glass formed by meteorite impacts. When an asteroid strikes Earth, the impact melts and vaporizes rock, then hurls some of it into the atmosphere. This material cools rapidly as it falls, forming glassy droplets and splash-shaped fragments called tektites. They are found in scattered fields covering large areas, often far from the impact crater itself. Tektites are typically black, green, or brown, with smooth aerodynamic shapes formed during their flight through the air. They contain no water or volatile elements, evidence of the extreme heat that formed them. Finding a tektite field helps geologists locate and date ancient impacts. The glass preserves chemical clues about the target rock that melted. Some tektites have been transported hundreds or thousands of kilometers from their source, testament to the energy of impact events. Each one is a frozen droplet of Earth's crust, briefly melted and flung skyward before solidifying in mid-flight. Turbidites are underwater avalanches preserved in rock. On steep underwater slopes, sediment can accumulate until it becomes unstable. Earthquakes or storms trigger these sediments to flow downslope as dense currents, like avalanches of mud and sand underwater. These turbidity currents can travel hundreds of kilometers, depositing their load of sediment in deep basins. The resulting deposits, called turbidites, have a characteristic structure. Coarse particles settle first, forming a graded bed that becomes progressively finer upward. Each turbidite layer represents a single event, a submarine avalanche that lasted hours or days. Stacks of turbidites build up deep sea fans and can reach thousands of meters thick. Geologists study them to understand ancient seafloor topography and to locate oil and gas reservoirs. They are records of catastrophic underwater flows, moments of chaos preserved in orderly layers. Underground rivers flow through limestone cave systems. In regions with soluble bedrock, rainwater seeps underground and flows through interconnected networks of fractures and caves. Some of these underground rivers are substantial, carrying as much water as surface streams. They can flow for tens of kilometers beneath the ground before emerging at springs. The water dissolves limestone as it flows, gradually enlarging the passages. Some underground rivers are accessible to explorers, vast, flowing streams in cathedral-like caverns. Others remain hidden, detected only by tracing water chemistry or using dye to track flow paths. These subterranean waterways are fragile ecosystems, home to unique species adapted to eternal darkness. They also provide drinking water for millions of people. Protecting them from pollution is essential because contaminants can travel quickly through the porous rock. Underground rivers remind us that not all of the water cycle happens at the surface, that entire river systems exist beneath our feet. Minerals can replace organic material cell by cell. Sometimes, when organisms are buried, minerals don't just fill voids, but actually replace the original tissue at a cellular level. Water, carrying dissolved minerals, flows through the buried material. As the organic compounds decay, minerals precipitate in exactly the same spaces, preserving the finest details of structure. Wood can be replaced so perfectly that individual cells remain visible under a microscope. Bones can be replaced while preserving the microscopic channels that once held blood vessels. This process, called permineralization when material is added, and replacement when the original material is removed, creates fossils of extraordinary fidelity. Scientists can study the growth rings in fossilized trees, the cell structure of ancient plants, and the bone microstructure of extinct animals. These fossils bridge the gap between life and stone, allowing us to see ancient organisms with cellular clarity. Mesas and buttes are remnants of eroded plateaus. In arid regions, flat-topped hills with steep sides rise from the surrounding plains. These features form when horizontal layers of resistant rock protect softer layers beneath from erosion. As the landscape erodes, isolated remnants of the former plateau remain. Large ones are called mesas, smaller ones buttes. The cap rock, usually sandstone or lava, is more resistant to weathering than the underlying shale or mudstone. As erosion removes material around the edges, the steep slopes retreat, but the flat top remains. Eventually, even the resistant cap rock is breached, and the whole structure erodes away. Monument Valley and the Colorado Plateau contain spectacular examples of mesas and buttes, the red stone forms rising dramatically against blue skies. They are witnesses to an ancient landscape, islands of stone showing where the land surface once extended. Each one is temporary, slowly shrinking as erosion continues its patient work. How light crystals grow in cubic shapes. Table salt or holite crystallizes in perfect cubes when it precipitates from evaporating seawater or salt lake brines. The cube shape is determined by the arrangement of sodium and chlorine atoms in the crystal lattice. Each cube is a miniature architectural wonder, with flat faces meeting at right angles. In some salt deposits, Individual crystals can grow to several centimeters across, clear or slightly clouded, stacking together like transparent building blocks. When you look closely at table salt under magnification, you can see the cubic form. Halite also shows cubic cleavage, meaning it breaks along planes that create smaller cubes. This property, like the crystal shape itself, is determined by the internal structure. Throughout human history, salt has been essential for preserving food and maintaining health. Every grain is a tiny cube, a fragment of evaporated seas, shaped by atomic forces into geometric perfection. Bedding planes record changes in depositional environments. Sedimentary rocks form in layers, and the surfaces between layers, called bedding planes, mark pauses or changes in deposition. Each plane represents a moment when conditions shifted. The environment might have changed from river to lake, from shallow to deep water, or from sand deposition to mud. Sometimes bedding planes show evidence of erosion, indicating that sediment was removed before new layers accumulated. Other planes preserve fossil footprints, raindrop impressions, or mud cracks, capturing surfaces that were briefly exposed before burial. By studying the spacing, thickness, and characteristics of bedding planes, geologists reconstruct the history of an area, reading the rock record like pages in a book. Each layer is a chapter, each bedding plane a paragraph break. Together, they tell stories of ancient environments that shifted and changed over millions of years. Pseudofossils are rock features that look like fossils, but are not. Sometimes minerals precipitate in patterns that resemble organic structures, creating shapes that look like plants, shells, or tracks, but are entirely geological in origin. Dendritic manganese oxide deposits on rock surfaces can resemble ferns or mosses. Concretions can look like eggs or bones. These pseudofossils have fooled observers throughout history, leading to mistaken claims of life in unlikely places or times. Distinguishing true fossils from pseudofossils requires careful examination. True fossils usually show fine anatomical details, consistent structure, and occur in appropriate geological contexts. Pseudofossils, while sometimes strikingly lifelike, lack these features when examined closely. They remind us that nature can create patterns that mimic life through purely physical and chemical processes. The tendency to see familiar forms in random patterns is deeply human, but it makes careful observation and analysis essential in paleontology. Geodes form when minerals precipitate in hollow cavities. Within some rocks, gas bubbles, fossil voids, or dissolved pockets create empty spaces. Over time, groundwater seeps into these cavities, carrying dissolved minerals. As the water evaporates or its chemistry changes, minerals begin to crystallize on the inner walls. Layer upon layer accumulates, growing inward. The result is a geode, often lined with sparkling crystals. Quartz, amethyst, calcite, and other minerals create stunning displays inside these natural treasure boxes. The outer shell is usually plain, giving no hint of the beauty within. Breaking one open is like discovering a secret world. Some geodes are small enough to hold in your hand, others large enough to walk inside. They form over thousands or millions of years as patient water works its slow magic, molecule by molecule, building crystalline chambers in the heart of stone. Ice ages are triggered by subtle changes in Earth's orbit. The planet's climate swings between warmer periods and ice ages in cycles lasting tens of thousands of years. These cycles are driven by small variations in Earth's orbit and axial tilt, called Milankovitch cycles. The orbit becomes slightly more or less elliptical. The tilt of the axis changes by a few degrees. The direction the axis points shifts over time. None of these changes significantly affects the total amount of sunlight Earth receives, but they alter how that sunlight is distributed across seasons and latitudes. When northern summers are cooler, snow persists year-round, building into ice sheets. These ice sheets reflect more sunlight, cooling the planet further in a feedback loop. Eventually, orbital changes reverse. Ice melts and warmth returns. We are currently in a warm, interglacial period. The cycles will continue, written into the planet's motion through space. Conglomerate rock is ancient gravel cemented together. When rivers carry gravel and pebbles, they eventually deposit them in areas where the current slows. Over time, more sediment buries these gravel beds. Minerals dissolved. In groundwater, precipitate between the pebbles, cementing them into solid rock. The result is conglomerate, a rock made of rounded stones embedded in a finer matrix. Each pebble in a conglomerate tells a story. Its composition reveals what kind of rock it came from. Its roundness indicates how far it traveled. Geologists study conglomerates to understand ancient river systems and mountain ranges. The pebbles themselves might be older than the rock that holds them. Fragments of even more ancient landscapes, broken down and transported before being cemented into new stone. Conglomerate is geology's way of recycling, taking old rocks, breaking them down, moving them, and building them into new formations that will themselves someday erode and join the cycle again. Transform boundaries are where plates slide past each other. At some plate boundaries, tectonic plates neither collide nor separate, but slide horizontally past one another. These transform boundaries experience intense friction as massive sections of crust grind together. The San Andreas Fault in California is a famous example. The Pacific Plate slides northwest past the North American Plate at several centimeters per year. This motion is not smooth. The plates lock together, stress builds, and suddenly they slip, causing earthquakes. Transform boundaries create linear valleys and offset streams where the motion displaces the landscape. Over millions of years, features on opposite sides of the fault can be displaced hundreds of kilometers. These boundaries remind us that plate motion is not just about creating or destroying crust, but also about plates moving past each other, their friction and sudden slips producing some of the most earthquake-prone regions on Earth. Paleomagnetism helped prove continental drift. When Alfred Wegener proposed in the early 20th century that continents had moved, most scientists were skeptical. The discovery that rocks record the direction of Earth's magnetic field at the time they formed provided crucial evidence. By measuring the magnetic orientation in rocks of different ages from the same continent, scientists found that the magnetic poles appeared to have wandered over time. But the simpler explanation was that the poles stayed relatively fixed while the continents moved. When paleomagnetic data from different continents were compared, the paths of apparent polar wander matched only if the continents were reassembled into their former configuration. This elegant proof, combined with seafloor spreading evidence, convinced the scientific community that continents do indeed drift. Paleomagnetism turned invisible magnetic fields into a tool for reading Earth's history, proving that the ground beneath us is not fixed, but has traveled vast distances over geological time. Sedimentary structures reveal the environment of deposition. The patterns and features within sedimentary rocks tell geologists about the environments where they formed. Cross-bedding, where layers are tilted at angles, indicates deposition by wind or water currents. Ripple marks suggest shallow water or beaches. Mud cracks mean the sediment dried out between periods of water coverage. Graded beds where particle size decreases upward indicate settling from a single event like a turbidity current. Fossil assemblages show whether the environment was marine, freshwater, or terrestrial. By reading these clues, geologists can reconstruct ancient landscapes in remarkable detail, determining whether an area was a desert, a river delta, a shallow sea, or a deep ocean floor. These interpretations allow us to create maps of ancient Earth, showing where continents stood, where oceans lay, and how life adapted to each environment millions of years before humans appeared. Certain rocks contain trapped pockets of ancient seawater. Within some minerals and rocks, tiny fluid inclusions preserve samples of water from when the rock formed. These microscopic pockets, sometimes visible only under a microscope, contain actual ancient seawater, complete with dissolved salts and gases. By carefully extracting and analyzing these fluids, scientists can determine the temperature and chemistry of ancient oceans. Some inclusions are billions of years old, offering direct samples of Earth's early hydrosphere. Others contain trapped bubbles of gas, providing samples of ancient atmospheres. Fluid inclusions are time capsules in the most literal sense, fragments of vanished seas sealed within crystal prisons, waiting for modern instruments to release their secrets. They connect us directly to environments that no longer exist, allowing us to taste the chemical composition of oceans that lapped against shores billions of years before the first life emerged. Selenite is a transparent form of gypsum. When gypsum crystallizes slowly from mineral-rich water, it can form large, transparent crystals called selenite. The name comes from the Greek word for moon, reflecting the crystal's pale, glowing appearance. Selenite crystals can grow to impressive sizes, sometimes several meters long. They are soft enough to scratch with a fingernail, and they cleave easily into flat sheets. In some locations, entire caves are filled with selenite formations, creating chambers of transparent stone that catch and refract light in beautiful ways. The Cave of Crystals in Mexico contains selenite beams larger than telephone poles, though these are often called gypsum crystals rather than selenite in scientific literature. Selenite has been used historically for windows before glass became common. Its transparency and the ease with which it splits into thin sheets made it practical for allowing light into buildings while keeping out weather. Rock flour is finely ground sediment from glaciers. When glaciers move, they act like enormous mills grinding bedrock into incredibly fine powder. This rock flour is so fine that it remains suspended in meltwater, giving glacial streams and lakes a distinctive milky turquoise or gray color. The color comes from the way the tiny particles scatter light. Rock flour is rich in minerals because it is freshly ground from bedrock, and it can be fertile when deposited on land. Glacial meltwater carries rock flour into lakes and oceans, where it settles slowly, building up layers of fine sediment. In some regions, wind picks up dried rock flour and deposits it as loess, creating thick, fertile soils. The process is ongoing wherever glaciers exist, continuously producing fresh mineral flour from the patient grinding of ice against stone. Every turquoise glacial lake owes its color to countless microscopic particles of pulverized rock suspended in its water. The principle of superposition states that in undisturbed layers, older rocks lie beneath younger ones. This seems obvious now, but it was a revolutionary idea in the development of geology. Nicholas Steno articulated this principle in the 17th century. If sedimentary layers have not been overturned or severely deformed, the bottom layer was deposited first and is therefore oldest. Each successive layer is younger than the one beneath it. This simple rule allows geologists to determine the relative ages of rocks and fossils without needing absolute dates. By applying superposition along with other principles like cross-cutting relationships, where features that cut across rocks must be younger than the rocks they cut, geologists can construct detailed histories of regions. These principles formed the foundation of stratigraphy and allowed scientists to piece together Earth's history long before radioactive dating was discovered. They turned rock layers into readable records of time, each one resting upon the past. Some minerals glow after being exposed to UV light. Phosphorescence is the property some minerals have of continuing to glow even after the UV light source is removed. Unlike fluorescence, which stops immediately when the light is turned off, phosphorescent minerals absorb energy and release it slowly over time. The glow can last from seconds to hours, depending on the mineral and how long it was exposed. Willemite and calcite often show strong phosphorescence, glowing green or orange in the dark. The phenomenon occurs when electrons in the crystal structure are excited to higher energy states and then slowly return to their ground state, releasing light in the process. Phosphorescent minerals were once used to make glow in the dark materials before modern phosphors were developed. They demonstrate that minerals can store energy and release it later, acting as natural batteries that charge with light and discharge with a ghostly glow in darkness. Druzy is a coating of tiny crystals on a rock surface. When mineral-rich water evaporates from a rock surface or cavity, it can leave behind a sparkling crust of tiny crystals. This druzy coating glitters when light hits it, creating a shimmering effect. Quartz druzy is common and popular in jewelry, but many minerals can form druzy surfaces. The tiny crystals form because the surface area allows many nucleation points, resulting in numerous small crystals rather than fewer large ones. Druzy coatings often line the interiors of geodes or cover the surfaces of broken rocks in mineral-rich environments. The effect is beautiful, transforming ordinary rock into something that sparkles and catches the eye. Each tiny crystal in a druzy coating is perfectly formed, a miniature gem that contributes to the overall glittering effect. Together, thousands of these microcrystals create surfaces that look like they have been dusted with diamond powder or frozen in mid-sparkle. Volcanic bombs are blobs of lava ejected during eruptions. When explosive volcanic eruptions throw molten rock into the air, it can cool and solidify during flight, forming projectiles called volcanic bombs. These take various shapes depending on how they spin and deform while airborne. Spindle bombs are elongated, twisted by rotation during flight. Ribbon bombs flatten into curved shapes. Bread crust bombs crack on the surface as the interior continues to expand. Some bombs can be several meters across and weigh tons. They land with enough force to create craters and can be thrown kilometers from the vent. Fields of volcanic bombs surrounding a crater tell stories of past eruptions, their shapes and distribution revealing the power and style of volcanic activity. Despite their violent origins, many bombs are beautiful objects, twisted sculptures of frozen lava that capture a moment of flight between liquid and solid, between fire and stone. The rock cycle connects all three rock types in a continuous process. Igneous rocks form from cooling magma. When exposed at the surface, they weather and erode into sediment. That sediment compacts into sedimentary rocks. When buried deep and subjected to heat and pressure, those sedimentary rocks transform into metamorphic rocks. If heated further, metamorphic rocks melt into magma, which can cool into igneous rocks again, completing the cycle. But the cycle is not simple or linear. Rocks can skip steps. Igneous rocks can be metamorphosed directly. Metamorphic rocks can be weathered without melting. Sedimentary rocks can be uplifted and eroded before being buried again. The cycle operates on timescales of millions to billions of years. Every rock is part of this cycle, temporary in its current form, destined eventually to be transformed into something else. The atoms in your body may have cycled through this process many times, having once been part of rocks that no longer exist. Certain clays shrink when they dry and form polygon patterns. Smectite clays contain water between their crystal layers. When this water evaporates, the clay shrinks significantly. In mud that dries on a flat surface, this shrinkage creates stress that is relieved by cracking. The cracks typically form polygonal patterns, often hexagons, similar to the way cooling lava forms columnar joints. The size of the polygons depends on the thickness and composition of the mud layer. Small mud cracks might have polygons a few centimeters across. Large ones can span meters. When ancient mud dried and cracked, then was covered and preserved, these patterns were fossilized. Modern mud cracks forming in similar environments help geologists interpret ancient ones, understanding what conditions produced the cracking and what the climate was like when the sediment was exposed to air. These humble patterns connect present and past, showing that the same physical principles have operated throughout Earth's history. The Earth loses heat left over from its formation. When our planet formed from the collision and accumulation of countless smaller bodies, the energy of those impacts was converted to heat. The Earth began as a molten ball, radiating heat into space. Over billions of years, it has cooled, but the process is slow. The core and mantle are still hot, and heat continually flows from the interior toward the surface. This heat drives plate tectonics, powers volcanoes, and creates the magnetic field. Radioactive decay of elements like uranium, thorium, and potassium adds more heat to the interior, slowing the cooling process. Eventually, perhaps in billions of years, the Earth will cool enough that plate tectonics cease and the magnetic field shuts down. But for now, our planet remains geologically active, a cooling but still hot world, releasing its primordial heat through countless vents, hot springs, and volcanic systems, and through the slow stirring of its interior that moves continents and builds mountains. Every rock tells a story if you know how to read it. The color, texture, mineral composition, and structure of a rock all provide information about its history. A geologist can look at a rock and determine whether it formed from cooling magma, settled sediment, or transformed under pressure and heat. They can estimate the temperature and depth at which it formed, whether water was present, how long it took to form, and what happened to it after. They can tell if it was once buried and then uplifted, if it has been fractured and healed, if it traveled far from where it formed. Rocks are archives, silent witnesses to events millions or billions of years ago. They carry information about vanished oceans, ancient climates, extinct life, and the slow dance of continents. Learning to read rocks is learning to read time itself, to see in a pebble the history of worlds that came before. It is one of geology's greatest gifts, the ability to look at stone and see deep time written in its structure, a language older than words, older than life, as old as Earth itself. The world beneath you is always moving. Even now, as you rest, the ground turns slowly under stars that once forged the minerals in your bones. Beneath the quiet crust, molten rock flows in endless cycles, shaping continents that drift like slow clouds across a sea of stone. Geology reminds us that change does not always roar. Most of it whispers. Mountains rise grain by grain. Oceans open wider than memory can hold. Every pebble, every crystal, every grain of sand carries the trace of time so vast that our own stories seem like brief flashes of light. Yet those flashes are part of the same pattern, written into the same fabric of the planet itself. Somewhere deep within the earth, pressure builds. Somewhere else, it eases and a new rock begins its long transformation. Far above, wind grinds stone to dust, and that dust drifts across oceans to feed life. Everything that ever was becomes something new again. The planet breathes in the slow rhythm of stone, and we breathe with it without even knowing. You might think of the places you have walked, the sound of gravel beneath your feet, the roughness of a cliff face, the warmth of sand between your fingers. Each is a story told in minerals shaped by time and touch. The world is not just alive on its surface. It lives within itself, turning memory into matter, turning silence into form. As you drift towards sleep, let that thought sink in like rain through soil. Imagine the deep pulse of the planet beneath you, ancient and steady. Let it quiet your thoughts and slow your breathing. You are part of this story, too. A brief moment in a vast, unfolding world that remembers everything. If you enjoyed this quiet journey, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. For now, just breathe. Let your eyes grow heavy. Let the planet cradle your thoughts. Still patient and eternal. Sleep well and good night.